Hello everyone, my name is Leandro Iannacone and I'm a PhD student at the University of Illinois at Urbana-Champaign. The title of the presentation is Stochastic Differential Equations for Modeling Deterioration of Engineering Systems and Calibration based on Structural Health Monitoring. This work is part of an undergoing research that I am conducting at the University of Illinois under the supervision of Professor Paolo Gardoni. The presentation will be structured as such. First, I am going to provide a brief introduction on deterioration of engineering systems, how deterioration affects them, and why it's important to develop tools for calibration of engineering models. Then, I will continue with the novel mathematical formulation that we have been developing at the University of Illinois, which will be followed by a brief application on synthetic data. Then, I will finish my presentation with some concluding remarks. Engineering systems are typically subject to aging and deterioration processes that impair their ability to sustain given demands. Deterioration models can help predict the performance of these systems, but their form and the value of the associated parameters are generally very hard to define. However, we can use non-destructive testing and structural health monitoring tools to improve the understanding of the systems and the way they are evolving over time. Now, in general, provided that we have the design parameters for an engineering system, we can obtain its probability of failure, that is, its fragility, at the time of construction, which we're going to denote by t equal to 0. If we have preliminary models for deterioration, then we can also obtain the probability of failure of the system at any moment in time during its life cycle. Assume now that we perform either non-destructive evaluation or structural health monitoring on the system. The information coming from these techniques can be used in several different ways. First, we can use the information directly to update the fragility of the system at the time of the inspection, which we are going to denote with P equal to T star. But we can also use the result of non-destructive testing and structural health monitoring to assert the quality of our original prediction for the state of the system. This can be used to update the deterioration models for the processes that are assumed to be acting on the system. Finally, we can use the newly updated models to predict the performance of the system in the future. Or in other words, we can obtain the fragility of the system at times that come after the moment of the inspection. In order to take all these aspects into account, we have developed a framework that allows us to obtain the time-varying reliability of the system starting from the external conditions that the system is subject to. The key aspect of this framework is that we look at the deterioration of the state variables, denoted by xt, which represent important quantities of the system, such as geometric properties or material properties. This framework uses state-dependent formulations for the evolution of the state variables. In other words, the rate of change of x over time is a function of the value x itself. By adopting this type of formulation, we are able to investigate the effects of the possible interactions among different deterioration mechanisms. Once we have obtained the evolution of the state variables over time, we can relate it to the change in both the capacity and the demand for the system, which in turn can be used to estimate the corresponding deterioration at the performance level and predict the time-varying probability of failure. For the rest of the presentation, I will focus on the modeling of the evolution of the state variable x, which is a fundamental part of this framework. Usually, the evolution of the state variables is described using discrete models. In other words, the time domain is discretized in a series of arbitrary small intervals, and the evolution of the state variables is described by identifying the parameters that define the probability distribution of the so-called one-step increment. This type of formulation has several disadvantages. For example, no closed-form solution is available for the distribution of the state variables at any given moment in time. In addition, the parameters used to define the models depend on the discretization that we chose for the time domain, and the calibration process for these type of models can be extremely expensive in terms of computational demand. But most importantly, these formulations do not reflect the true nature of the deterioration processes, which is continuous. In order to overcome these limitations, we proposed a new formulation that models the evolution of the state variables with a system of stochastic differential equations. This slide shows the usual form for a stochastic differential equation. We can see how the infinitesimal increment in the state variable, the x, is given by the sum of two independent contributions. The first one quantifies the deterministic change in time of the state variable and is obtained by multiplying what we call the drift coefficient mu by the infinitesimal time interval dt. The second term quantifies the evolution over time of the uncertainty and can be obtained as the product of a so-called diffusion coefficient and the driving noise. I will go more into the detail of this driving noise, and I will show how different choices for this driving noise produce different results for the evolution of the state variables. Note that both the drift term and the diffusion term depend on the value for the state variables x itself, so that the formulation that we are proposing is indeed state dependent. The continuous formulation that we have proposed has a series of advantages. For example, the unknown parameters theta no longer depend on the discretization that we choose for the time domain. As a matter of fact, we don't even need to discretize the time domain in this case. In addition, results from stochastic calculus, which is also known as ethos theory, can be used for the simulation of the stochastic processes. This continuous formulation also allows to seamlessly combine the effect of gradual and shock deterioration in a compact form. And closed-form formulations, for example the ones for first passage probability, are available to perform a reliability analysis on the system. Most importantly, however, this type of formulation reflects the true continuous nature of the phenomena that are affecting the deterioration of the system. With this specifics modeling, the deterioration problem can be seen as a random vibration problem. For this type of problems, we can usually obtain the probability distribution of the variables over time using a differential equation, which is known in literature as the Fokker-Planck equation. The equation shown in this slide is the Fokker-Planck equation when the driving noise is a standard Brownian motion, which is an ideal choice in case the modeled processes do not exhibit jumps over the life cycle of the system. However, deterioration processes can be complicated. In particular, we can usually have jumps in the process due to shock occurrences. For example, the occurrence of an earthquake might cause a sudden deterioration of the state of the system. To accommodate as many behaviors as possible, we chose differential equations with a semi-martingale driving noise and nonlinear drift and diffusion terms. A semi-martingale is a particular type of driving noise which can be decomposed as the sum of a local martingale and an adapted finite variation process. The local martingale component in particular can be furtherly decomposed into two components, a Brownian motion component and a compensated Poisson process component. In particular, the Brownian motion component will be the one responsible for the part of the deterioration process that has no jumps. For example, the gradual deterioration, while the compensated Poisson process component will be the one responsible for the part of the process that exhibits jumps, that is, the shock deterioration processes. Semi-martingales form the largest class of processes for which both Ito integrals and Stratonovich integrals can be defined. In other words, by using a semi-martingale driving noise, we are able to accommodate nearly any possible behavior that our deterioration process might exhibit. However, because semi-martingale components are generally not square integrable, the regular Fokker-Planck equation that I showed earlier cannot be used in this case. Fortunately, we can obtain a partial differential equation for the characteristic function of the probability distribution of the state variables over time. This differential equation is shown here and will be key in the calibration procedure for the deterioration models that will be proposed. In fact, this equation has a set of unknown parameters, theta, that define the behavior of the deterioration process. The idea here is that if we could obtain n snapshots of the characteristic function over time, We could think of back calculating these unknown parameters by performing a minimization problem. For example, here we show the set of parameters theta obtained as the one that minimizes the norm of the difference between the characteristic function that is computed from the differential equation, which we denote by phi, and the characteristic function that is observed, which we denote by phi star. But how can we obtain these snapshots of the characteristic function? We could think of using the results obtained by performing non-destructive testing or structural health monitoring on our system. Assume, for example, that information is collected periodically over the life cycle of the structure. Several methods exist in literature to fit a probability distribution to a set of collected data. For example, mixture models use a set of k different probability distributions from a parametric family, which is, for example, normal distributions, to which they assign different weights. In particular, a Dirichlet process mixture model has been recently developed at the University of Illinois. This mixture model is particularly flexible as it allows the number k of distributions to go to infinity. Once we have fit the distribution to the data collected during the inspections, we can compute the experimental characteristic function. This is simply done using the definition of characteristic function, which is none other than the Fourier transform of the probability density function. I am now going to show how the given procedure can be applied in a simple example. For this example, we generated data from a given stochastic process, which was a geometric Brownian motion in this case. Then we assumed that data were collected at 10 different inspection times throughout the life cycle of the system. After we collected the data, we forgot about the original process and we tried to use the information obtained to fit a model in the general form that we have proposed with this framework. With minimal loss of generality, we assumed that the nonlinear drift and diffusion terms could be expressed in polynomial form. Thanks to this assumption, we were able to simplify the partial differential equation that was shown earlier. The solution of this partial differential equation was compared with the observed characteristic function in order to minimize the difference between the two. The minimization problem reached convergence, and we tried generating new sample paths of the deterioration process with the new calibrated values for the unknown parameters theta. The results are shown in the figure to the right. As we can see, the sample paths go through the cloud of original data points. In other words, the calibrated model is able to capture the shape of the true model. Concluding, information about the reliability of engineering systems and the deterioration processes acting on them can be updated using results from non-destructive evaluation and structural health monitoring. The models available in literature are able to account for the effect on multiple deterioration processes, both gradual processes and shock processes, and also to account for their interactions. But the use of stochastic differential equations can facilitate both the simulation and the calibration of these models. The adjusted models can then be used to predict the state of the system at future times in a semi-closed form. Finally, using the predicted state, we can predict the future performance of the system, for example with time-varying fragility curves. That concludes my presentation. Additional information is available in the paper submission number 61, Stochastic Differential Equations for the Deterioration Processes of Engineering Systems. Thank you for your attention.